Our kickoff today after lunch is Professor Philip Lubin from the University of California, Santa Barbara, talking about his deep in directed energy propulsion. So hopefully he'll be able to wake us up nicely from lunch with that. That should be a great thing to get started with. So.
Great. Thank you, Jason. Okay, so we were chosen for phase one. The project is sometimes called DEEP or Deep In. It's a directed energy mission using an extremely small spacecraft, although it can drive any size spacecraft. And it is the only realistic way I know to get to relativistic speeds and to achieve even the beginnings of interstellar capability. We heard this morning from Mr. Beers, I think is his Bears, maybe? Bears. About throwing stuff out the back end of the exhaust pipe, and that is generally not going to get you anywhere near relativistic speeds with anything that we know how to do. But this does have that capability. I hope to convince you that it's more than science fiction, but can be made into science fact. All this stuff's on our website, so feel free to visit us. So we were chosen for phase one in June. I'm going to show you both some simulations and some experimental results from the laboratory. We were chosen to explore using directed energy in a feasible way, rather than just in a hypothetical way, and to explore the use of extremely small spacecraft. In fact, we're proposing to put a spacecraft on a wafer, at least functionally, to have many of the aspects of a traditional spacecraft, but on a wafer scale, and to develop a roadmap to interstellar flight rather than just talk about it as it's done in movies or in many of the science fiction books that we all so love, and to explore the technological limitations and what the various TRL levels are, which I'll explain to you. And then I'll talk a little bit about methods for improving the performance using photon recycling, which I'll show you some results we have from the laboratory. And then I'll talk a little about the many other uses for this technology. It really is a transformative technology which allows you to do things way beyond anything that's conceivable at the moment, including things such as mitigating storms, for example, terraforming on Mars, planetary defense from a complete standoff capability or stand-on capability. So there's a lot of different slides here, and I'm going to blow through some rapidly and spend some more time on those. Within about 25 light years of the Earth, there's actually quite a few potential exoplanets and habitable things to visit that may be habitable. We don't know, of course. And so there are many targets to choose from. The closest is Alpha Centauri, which is about 4 light years away. So we'll focus on that. But there are a number of targets within reach of a human lifetime that I'll explain. So here's the dilemma. We know how to get to relativistic speeds in the laboratory. We do it all the time, literally. In the laboratory, every single day of the year, every year since many decades ago, we've been at greater than 99% the speed of light with some particle. And yet when we go to the macroscopic level, we go from microscopic, where it works really well, over here, we get to actually within 1 meter per second of the speed of light. And then we go to the macroscopic level over here, where things like aircraft, cars, spacecraft, were pathetically slow. And in between, there's nothing. So the question is, can we bridge that gap between what we do now on the macroscopic level with chemical binding energies, which are about 1 eV per molecular bond, to relativistic speeds, which are done with electromagnetic acceleration? And so that's a higher level view of thinking about this whole problem. And we would claim that divide can be filled with a directed energy approach. Okay, so photon-driven propulsion is not a new idea. It goes back to the beginnings of thinking about light in both the classical and the quantum mechanical way. You get about 6.6 nanonewtons per watt for a single reflection off of any surface. And if you want to scale that up, for example, the shuttle, when it would take off, or the SLS, when it will take off, will have a power off the launch pad of between 50 and 100 gigawatts. We normally specify it in pounds of thrust or newtons of thrust, but we could also talk about in terms of power. It turns out to get to relativistic speeds with the spacecraft we're talking about, you need basically the same power level. And for about the same amount of time. It takes 10 minutes to get to orbit with shuttle. It takes us 10 minutes to get to 30% the speed of light with about the same power level, just using different technology. So as an example, a little teaser, we could propel a 100-kilogram robotic craft to Mars in a few days and be going at greater than the galactic escape velocity, so about 1,200 kilometers per second, which is vastly faster, by the way, than Voyager's going, which is about, I guess, 17 kilometers per second currently. We could get overnight express to Mars with a kilogram package if you want. Amazon might want to take note of that if anybody's from Amazon here wants to deliver quickly. You don't need a quadcopter. We'll do it for you. We won't guarantee the delivery condition, but we'll get it there. It takes about 8 hours to get to Mars with a kilogram. And if you want to push something like shuttle class, it takes you roughly of order a month to get there. So this is used for not just tiny things, but it can be used for anything. So that's the one thing we need to talk about is the amortization of the cost of such a system, because you can drive any class of payload. Okay. So in a cartoon form, this is what it looks like. You're basically pushing on a reflector. The light exerts a force. You leave your propulsion system at home. There's nothing to spit out the exhaust pipe because there is no exhaust pipe, just a reflector and a spacecraft. Eventually get far enough away that the beam divergence overfills the reflector and the efficiency slows down, becomes less. There's a paper out there called A Roadmap to Interstellar Flight, which is also on our website. You might want to take a look at it if you're interested in the mathematical details. This is kind of what it looks like from an undergraduate artist conception, which I thought they did a very nice job on. Lots of plots for your thoughts in our papers. They're filled with them. I can't help it because I love plotting things and calculating, so lots of calculations. Basically, this covers everything from a CubeSat demo up to a full-blown system. So here's a 1 kilowatt, 10 centimeter array, which is about the limit of what we can do on a CubeSat. And I'll explain that to you offline if you're interested. Up to a full-blown system for relativistic speeds, it requires about a 10-kilometer class array. And I'll explain how we do the optics. The optics are done as a phased array. It's a phased array approach, which 10 years ago was not really feasible, but is feasible today, and in fact is being done quite successfully, particularly in certain types of systems for programmatic purposes. Okay. So this is very real. The devices that exist today, they're actually extremely efficient. As of about 2 months ago, the efficiency of the pumps was pushed to over 50%. It's 55% now. And the total system efficiency is pushing above 40%. And this will keep rising. Currently, it's 5 kilograms per kilowatt. You could hold a 1 kilowatt laser amplifier in one hand. It will soon be 1 kilogram within about 2 to 3 years. It's already on a path forward. Okay, and the coherence time is sufficient to build an array this size. The phase noise looks low enough. There does not appear to be a showstopper. I've gone over and over with many, many people in the field. Does not appear to be a reason why we can't do this. This is an efficiency curve. These devices are amazingly efficient optically, close to 90% efficient optically. And this is what one looks like. It's about the size of a book, and will soon be much smaller than that. This is a Moore's Law-like curve that I plotted up. This is laser power coming from a single fiber versus time over 25 years. Doubling time is every 20 months approximately. Amazing curve. It already exceeds what we need per element. We only need about 1 kilowatt per element. We're already well above that. Lightweight optics for the full system becomes an issue. This is a DARPA program that produced thin film optics, which looks sufficient for us because we're quite narrow band. Didn't work very well for them, but it would work well for us, it looks like. It's basically a holographic or Fresnel lens. And we did some measurements in laboratory this summer. One of the things about this program is it is incredibly attractive to students. When you tell them you get a laser and you can blow holes through whatever you want, they just come flocking to your door. And they want to punch holes through anything, including their roommates' things. So we built a vacuum chamber to simulate space, built a really high stability torsion balance and with a laser readout, and put in a nice IR reflecting mirror, which doesn't reflect very well in the visible, but this is it. And And this is what the curve looks like. This is a 1,000 sigma result, which I've never seen 1,000 sigma before, but this is literally a 1,000 sigma result pushing on the mirror. Nothing exceptional here, but just part of the process of looking at this in detail. Then we went into photon recycling. A single photon bouncing back and forth between two mirrors can impart an arbitrarily large force on both mirrors. Arbitrarily large. Arbitrarily large. It could be 1,000,000 newtons of force from a single photon. And you say, how's that possible? Because the momentum is conserved. Just because there's force on one means there's almost an equal and opposite force on the other. Okay? So you're not violating anything. So we could actually exceed the force of chemical reactions this way if we wanted to, if we could. So if we had greater than 10 to the 5th reflections, we would exceed existing chemical propellants, which means we could lift large things off the ground. That is actually possible in the laboratory to do, by the way. LIGO, for example, has 6 nines reflectivity all the way already over a 4-kilometer path length. Okay? So there are some practical limitations to doing this, and I don't want to get into details of it, but just all the pieces might be in place for doing this. I'm not assuming any of this in what I'm going to show you. I'm not assuming any photon recycling. Okay, this is a photon recycling curve that we did in the laboratory this summer. We got about a factor 10. And that was for almost no effort. So I'm not assuming any of this in the results I'm going to show you, but looks like it might be an interesting approach. Okay, when you shoot a small spacecraft out of, say, out of the Earth's low Earth orbit, it basically just goes straight out because the force is so high on such a low mass. So this is what happens in terms of the XY plane. This is an AU, and these are 10-minute increments. In this case, it's a 1-meter reflector with a wafer on it. It accelerates at 30% speed of light in 10 minutes. Next wafer. Every 10 minutes you have a launch. About 40,000 wafers per year if you want. You could put one for every square degree on the sky. This is a putative system, one which is a long-term goal. This would be an interstellar probe. You would pass Mars in about 30 minutes, pass Voyager in 3 days, get out the solar lens focus in about 6 days, and 1,000 AU in 12, get to Alpha Centauri in approximately 17 years. So that would be sort of our long-term goal, but that's not where we're starting. Okay. Another offshoot of this is actually quite an interesting thought, which is if we have the technology to do this now, and there's nothing that prevents us from doing this, it's just a matter of will. The technology looks like it's in place. Launching enough elements in space is a problem. Getting enough launchers to put it up is the issue. The mass in orbit is about 100 times the ISS mass. So it's significant, but it's not completely crazy, at least over, say, a 50-year time scale. The question is, if we have this technology, what if some other civilization had this technology? What would be the implications of that? And the answer is, in a paper that we're about to publish, called The Search for Directed Intelligence, as opposed to the misdirected intelligence that some of us know about in certain places. The answer is you can see across the entire horizon. There's 2 civilizations that had this capability, could see easily to redshift 10, which is a profound statement if you're a SETI person. So this is a signal-to-noise plot, which if you're interested, you can talk to me afterwards. Okay, we propose a roadmap. Start small, like we've started small in the laboratory, and work your way up the food chain. So we call these by a dash number, which is the logarithm of the size in meters. So a -1 is a CubeSat, is a 0.1 meter. A 0 is a 1 meter, a 1 is a 10 meter, a 2 is a 100 meter, et cetera. So we propose a logical roadmap to work your way up the food chain. Don't do it all now. Use the fact that there's a economy of scale here. And I want to talk a little about economies of scale because this is very important. A lot of people look at something like this and they say, how could you possibly do that? Well, go back to the 1960s and ask someone, how many computers do you need in the world? And I'm sure you've all heard this story. And the answer was, oh, probably 5. Okay? And that was just not being thoughtful enough. So let's look. Here's the historical trends, which is sometimes called the Swanson plot of photovoltaics. Something very practical, something you're very used to. Over a not very long time period, this is from 1976, and this is actually dollars at the time, not in real dollars, so it's even worse. So this is approximately 4 decades of cost reduction, over 4 decades of time, there's about 3 orders of magnitude cost reduction. Okay, that's interesting, and something which is closely aligned to this. This is photonics. Here is 6 decades of time for the computer industry, which we had 11 orders of magnitude decrease in price per unit here, which was memory cost. Again, no one in the 1950s who wasn't in an insane asylum would have been taken seriously that this would occur. Here's 115 years, from 1900 to 2015, of computing cost calculations per $1,000. 17 orders of magnitude. Yes, I'm about to finish up here. Yeah, I'm cognizant of that. Thank you, Bill. 17 orders of magnitude. If you went back to the year 1900 and predicted that people would carry around, gigaflops on their, thing, they would have, locked you up for being insane. Okay, so here's the conclusions, which I think need to be talked about and thought about seriously. There are recent advances which take this from science fiction to science reality, and they need to be appreciated if you want to understand this properly. There is no known reason why we cannot do this, except for a NASA budget reason. Okay. There's a roadmap, which you can look at in our paper, to relativistic flight. The system is completely scalable modularly. Build any size you want, from a tiny one to a gigantic one. Okay, this allows for an economy of scale. All the modules are the same, which allows mass production and therefore radical cost reductions. So we propose trying to be logical about this. We also enable many, many missions with a single driver. So we talked earlier about the cost of a single starship and what happens if it fails. If one of these fails, so what? Doesn't really matter. Okay, is it hard? Yes, it's hard, otherwise NIAC wouldn't have been interested. Is it impossible? Well, the answer must be no, otherwise NIAC wouldn't have funded it, right, I guess. So, all right, not for the faint of heart, right? But we believe that it's time to begin to seriously look at this. And if you're interested, check out our stuff, come talk to us. We're always interested in collaborators, and I will stop there.
All right, so we have a little more than 7 minutes for questions, including from the live stream audience. So,
yeah, I want to borrow your laser. I have a deck in Seattle.
You want a real laser?
I have a deck in Seattle, and the neighbors down the block are growing trees that block our view of Mount Rainier. So.
Oh yeah, this is great for that. It's also good for taking out your neighbors that you don't like. So.
First of all, your business about infinite.
Well, I wouldn't say infinite
forces,
scalability, but
doesn't really take into account the Doppler shift when you're accelerating this thing away, does it?
Okay, so I chose my language very carefully. I said that you could exert an infinite force on 2 mirrors. Once they begin to move, then the force decreases, as you say, because of Doppler shift. So we work out actually what happens as they start to move. And of course, you're not going to get out any more momentum than the momentum you put in. So if you have an infinite mass mirror on one side and a zero mass mirror on the other side, guess what speed it gets to?
Yeah.
The speed of light. Right. So, but if you have 2 stationary mirrors, you can have an arbitrarily large amount of force, which is interesting.
The other thing is the reflector at the end of this 6 gigawatt thing had better be 100% effective in reflection. Otherwise, you're going to eat a lot of that 6 gigawatts.
And that's exactly right. So if you look in our paper, you'll see a plot of the absorption coefficient for glass. So Z-blan, which is a particularly low absorption coefficient glass, has 1 part per trillion per micron thickness. So if you put a terawatt on it, and it's a micron thick, it'll absorb 1 watt. And it's already the type of materials used in fiber optics. So I'll give you an example. At the tip of a fiber optic for the cable that this comes out of, which is about 20 microns, is much greater than the flux on our reflector, much greater. And you know they work because they work.
Okay.
Okay. But we've thought about that, and if you want to take a look, we have some plots for that. Yes. Hi, Lou. I think I know you.
So, as you know, I love this, and you've already...
You do. You just hate my plots.
No, and you've already influenced some good ideas about...
he's already plotsed over it.
Yeah, taking good things. I think the next thing we got to do is, and I'm encouraging in the next phase, to get the scientists who have mission objectives that they want to do. It's one thing to have the technology that enables it. Now the next thing is, what do you want to do with it? And there's, as you know, we've been working on the idea of what are the interstellar precursor targets that go along with D star -1, D star 0, D star, and so forth. What are the targets? The interstellar medium, the solar gravity lens focus, 1000 AU, Oort cloud, things you can do at these places that will sort of give everybody the sense that we are moving out to that direction. So otherwise, we're just developing.
I completely agree. So we were looking at a putative, Alpha Centauri flyby mission because we're not stopping. Okay, just if you've ever watched Spaceballs, on the back it says we stop for nobody. Okay, so we stop for nobody. But the nice thing about this is you can propel anything you want. 100 kilograms, 1,000 kilograms, 1 kilogram. And so, any mission that you could imagine fitting into the mass for a given speed, in theory would be a candidate. There are lots of issues. This is not a simple project. This is a long-term goal of humanity from my point of view. And this is something which has a roadmap to it. Absolutely. I mean, if you want to start can you just start the video running? I'll show you a very small array in space. Just you can see it in the background, how it kicks an object from low Earth orbit out of Earth orbit for a relatively small. This is actually a 15-meter system in space in low Earth orbit. Pardon? Yeah, not quite. So over successive orbits, you kick it out, you'll see it go out. It goes out of the Earth system. And this is a small one. This is smaller than a weapons system, which is already will be built next couple of years. So,
well,
yes.
The weapons systems are, of course, driving the underlying technology.
You're not supposed to say that. I didn't
Yes.
say that. Oh, I just said that. Sorry. Yes.
But of course, one element of your slide is debris avoidance and debris removal.
Correct.
And of course, that's a major thing.
Correct.
I was wondering how this compares with the calculations done for microwave interactions, for microwave propulsion.
Yeah. Okay. So it's basically, if you're familiar with the concept of forward gain, so the gain of an antenna goes inversely as the square of the wavelength. So meaning basically the solid angle that it subtends, or the amount of power you put in a given area. So the disadvantage of a microwave system is that you cannot get the same flux for the same aperture at the same distance. And the difference is quite profound. So let's say I have a millimeter wave gyrotron, which is just about the limit of what's possible for millimeter waves, which has a similar efficiency, by the way. A millimeter compared to a micron is 1,000 to 1. It goes as the square of that. We get 1,000,000 times more power on the target.
Well, the other argument in your favor would be the fact that you can get mirror reflection easier with your
Yeah,
materials.
there's a number of things. I do millimeter waves for a living, if you know what my real background in, which is cosmology. Okay, so I'm very familiar with millimeter wave technology. It's just in this application, I don't think it fits.
Well, if I can also make a little plug here, there's about 5 or 6 scenes in my latest novel that use exactly your technology.
Excellent. Okay. Any other questions before we? All right. Thank you.
So for those who don't know, that was Dr. David Bren. He's a member of the External Council. I think everybody here knows him, but we have our next speaker,